Delaware Tech, Chemistry 100, Chemistry 110, Unit 5 continued, reaction type number 5, combustion. We've already briefly mentioned combustion when we were doing the first introduction to balancing equations, but let's talk about it in a little more detail. Combustion is a carbon compound reacting with oxygen. We would say it's burning in the presence of an oxygen atmosphere. Now, you should know that combustion actually means even more different types of reactions to a chemist, but for the purposes of these classes, we're just going to consider only carbon-based compounds reacting with O2 gas to produce two products and two products only. And these two products are carbon dioxide and water, H2O. So the reaction would be some carbon compound. Maybe it has hydrogens. It usually does. Maybe it has oxygens. Sometimes it does. And it reacts with a certain amount of molecular oxygen, that is O2 gas, to produce, if it goes to completion, it will produce only CO2, carbon dioxide gas, and H2O, water. So if you look at the formula for this carbon compound, it has X number of carbons, Y number of hydrogens, Z number of oxygens, and Z might be 0. Okay, and here's an example of one particular combustion. This is CH4, or methane. You would learn it using nomenclature rules as carbon tetrahydride, but most chemists just call it methane, reacting with two O2 molecules to produce one CO2 and two H2O molecules. And you'll notice that all the atoms on the left balance all the atoms on the right. So this is actually the balanced equation form. You'll see that there is one carbon on the left side of the reaction, one on the right. There are 4 hydrogens on the left, and there are 4 hydrogens on the right because we have 2 waters that each have 2 hydrogens. And then we have 2 oxygen molecules, which means we start with 4 oxygen atoms, and we end up with 4 oxygen atoms. 2 of them are in the one CO2, and 2 of them, 1 each, are in each of the 2 waters. So this is a balanced equation for the burning of methane, the combustion of methane. So we're only going to be looking at complete combustion. So anytime you see a combustion reaction, that is a carbon compound reacting with oxygen gas, the only products formed will be CO2 and water. Notice that all the carbon in the carbon compound is turned into CO2, and all of the hydrogen in the carbon compound is turned into water. And this will help us when we're balancing the equations. So all our reactions are going to be assumed to be complete combustions. So in this particular example, we start with one molecule of CXHYOZ and an excess of oxygen gas. And how many CO2s are you going to form, and how many waters are you going to form? Well, if you have X carbons in your first compound, and you have one molecule of that, well, you'll make X CO2s, the same number of carbons that you started with. Every one of those carbons can make a CO2. Meanwhile, we have Y hydrogens in our starting molecule. And remember, each water form needs 2 hydrogens. So whatever the Y is, we just divide it by 2, and that tells us how many waters we have. Look at the example, CH4. We have 1 carbon, so we make 1 CO2. We have 4 hydrogens, so we make 4 divided by 2, or 2 waters. And this is how we're going to balance the equations. And we'll talk about how to calculate how many O2s are needed for this in a minute, but that's the general way to approach the combustion balancing of the equation. You figure out the carbons, you figure out the hydrogens, and that will tell you the CO2s and the waters. And then once you know how many oxygen atoms you need to make your CO2 and water, now you know how many O2s you need to do your reaction. So, if an atom appears more than one time on either side, balance it last. This is from the strategy I gave you once before, so oxygen is always going to be the last thing to balance. Carbon and hydrogen are the easy things. They appear one time on the left and one time each on the right. So those are easy to balance. You balance those first. The hydrogen's slightly harder. You could do that one first, and the carbon second, and then oxygen last. But it really doesn't matter if you do the carbon or the hydrogen first. They're equally easy to do. So here's a molecule, C6H8, and we're reacting it with O2 gas, always to make CO2 and water. Anytime you burn a carbon compound, and by the way, since this compound has only carbon and hydrogen, we call these a hydrocarbon. Hydrogen, carbon, hydrocarbon compound. And there are many, many hydrocarbon compounds, including methane, ethane, and even the octane you put in your gas tank. So if we start with one C6H8, we know we can make 6 CO2s because we have 6 carbons, and we can make 4 waters because we had 8 H's. That's enough to make 4 H2Os. So now the question is, how many O2s do I need? Well, it's 8, but let's figure out how you get to 8. So I'm showing you the answer, but look at the carbon dioxide that you're formed, and I'm going to highlight this here. You've got 6 CO2s. That means you need 12 oxygen atoms to make those 6 CO2s. And you're also producing 4 waters. Well, those 4 waters have a total of 4 oxygen atoms in those. So if we add these together, we see that we need 16 atoms of hydrogen. 16 atoms of hydrogen would be provided by 16 divided by 2 molecules of O2. And you'll notice at the end we have whole numbers, 1 to 8 to 6 to 4 ratio, and you can't simplify that anymore, and there are no fractions, so you're done balancing. You don't need to write the 1. We don't typically write the 1, so we would just write it as C6H8 plus 8 oxygens gives us 6 CO2s and 4 waters. And I'm going to erase these notes. But so sometimes if you fix everything but one element, and there's an even number on one side and an odd number on the other side, you have to double everything. Okay, what does that mean? Well, you saw how we counted up how many oxygens were in the 6 CO2s and how many oxygens were in the 4 waters. We had a total of 16 oxygen atoms. Well, with 16 oxygen atoms, it's easy to determine that we needed 8 O2s. You just divide 16 by 2. But what if we had an odd number of oxygen atoms? What do? Well, we can't divide it by 2. We'll get a fraction for the number of oxygen gases, and therefore that won't give us the correct balanced equation, not because it's not balanced, but because you can't have fractions in your final answer. So let's look at an example where something's going to go wrong. We have C4H10. This is actually butane that you put in a butane lighter. It could be one other molecule, but we'll worry about that when we get to organic chemistry. So you know from C4H10 that you can make 4 CO2s and 5 waters. And now if you look at the CO2s, that requires 8 oxygen atoms. And the 5 waters require 5 oxygen atoms for a total of 13 oxygen atoms. Now you can say, oh, well, if I have 13 O's, then I need 13 divided by 2 O2s. And that's perfectly fine as long as you get rid of the fraction later. Or you can say, okay, I have an odd number. How do I fix that odd number? Well, you fix that odd number by looking at the numbers you've already set, 1, 4, and 5, and doubling everything. So now it's 2, 8, and 10. And now when you recount your oxygens from the CO2, you'll have 16 O's here. And from the 10 waters, you'll have 10 O's here for a total of 26 oxygen atoms, which you can easily divide by 2 to get 13 O2s. And you would write 2 butanes react with 13 oxygen gases to make 8 CO2s and 10 water molecules. You'll notice that if you had just not doubled everything, you would have had a ratio. I'm going to erase some of these notes here. You would have had that 13 oxygens, and you would have divided it by 2 to get 13 O2s. Well, if you had done that, and I'm just clearing the board here, if you had done that, you would have gotten a ratio of 1 to 13 halves to 4 to 5, which is the correct ratio, but you're not allowed to have fractions, and the way to get rid of the fractions is to double everything by 2. So you could have doubled it, multiplied everything by 2. You could have multiplied everything by 2 once you determined it's 13.5 O2s, or you could have waited to figure out how many oxygens after you double everything, knowing that you'll get a whole number of the O2 molecules in the end. It's up to you how you want to approach it. There are actually several ways to approach this problem. Do it whichever way is more comfortable for you. So let's look at some examples. And most of these I'm going to have you do on your own. The first 3 of these you can do using the rules we already set. In this case, I'm going to tell you you won't have to double. In this case, you will have to do a 2x to get it. And in this case, you'll be fine. And now in this last case here, you'll notice there are oxygens in the starting material. Well, we know that our only products are going to be CO2 and water, so we can write that right away. In fact, that's what you should write it right away. We have 6 carbons. Oh, I can make 6 CO2s. We have 12 hydrogens. 12 divided by 2 is 6 waters. So now I know that I'm going to make 6 CO2s, which means I need 12 atoms of oxygen. I'm also going to make 6 waters, which means I need another 6 atoms of oxygen. That's 18 atoms. Now, if we look at the other side of the equation, I'm putting a squiggly line between the two sides, we've already set this as 1. So we know the starting material has 6 atoms of oxygen in it. And the final result will have 18 atoms of oxygen in it. Well, if we've already got 6 of our 18, we know that the O2 must provide the other 12 O atoms, the oxygen atoms. And if we only need 12 oxygen atoms from the O2, that means we need 6 O2s to do that. So our balanced equation will be one of these molecules, and by the way, this is the formula for glucose and a lot of other simple sugars. So if we burn glucose, we need, for every 1 molecule of glucose, we need 6 molecules of O2, and we will produce 6 molecules of CO2 and 6 molecules of water. Incidentally, doing this reaction is actually the same reaction that you do in your body and most living organisms do when they break down sugars during metabolism. You actually do this exact reaction, but in your body, this reaction takes dozens of biochemical steps to accomplish. It doesn't happen all in one shot like it would if you set the glucose on fire in the presence of oxygen. So I'll pause here for a second, and now I'll show you the answers. And with this, we'll end here.